Good evening, sir. Krishna Prasad, sir. Good evening, sir. Krishna Prasad, sir.
Yes.
Anthony.
Namaste. Yeah, I
Namaste.
can start the video.
Sir,
Just give me a minute.
Sure.
Sir, namaskara.
Namaskara. ಹೇಗಿದ್ದೀರಾ?
ಚೆನ್ನಾಗಿದ್ದೀನಿ sir.
Very good. Am I seen and heard?
Yes sir.
Okay, but the thing from your side is very low for some reason. It's 100% on my side. I don't know what the problem is.
Yeah, but ಕೇಳಿಸ್ತಾ ಇದೆ sir ಚೆನ್ನಾಗಿ.
Okay. From my side, if it is clear, then it's enough.
It is clear, sir. Start ಮಾಡೋಣ sir.
But you said 4:15. I'm ready anyway.
Okay sir. Another 5 minutes left. Okay. Students are joining.
Okay.
Sir, you may keep your PPT ready, shared.
I have it ready. I can probably even share it just to see whether things work all right or not.
Sir. Yes. Open your PPT first, sir. Then
I have
then
opened.
go to share.
I have opened
Now,
and
click on the share button on Cisco WebEx.
yes, I have.
It will ask you the window. Yeah. Now go
Do
to
you
full
see
screen,
it?
sir.
Do you
Yes.
see it?
Please go to full. Yes, sir.
Okay. Because for some reason I'm not seeing
Go
that.
Down. Come down, sir.
I wanted to be seeing the participants as well as simultaneously stop review. Why is it showing me in a small this thing? So where is the shared?
Down.
Pardon?
Near the zoom in, there is a mark. Sir, you have notes, comments, one
Yeah, I
section,
have
not
more.
down.
More.
Note,
What do I
comment.
do?
Beside that, there is a sign to go to full screen.
Full screen for participants.
Yes.
You see the full screen?
Not that, sir. On your PPT, I'm saying. Where you open the PPT.
The PPT on full screen.
Yeah.
Just 1 second. Is it okay now? No, not yet, I guess. Yeah.
Yeah, the
Is it
other
for
one.
me?
Yes. Now,
Okay.
yes.
Okay.
Okay. Keep the first slide, sir.
Pardon?
Keep the first slide. Top one.
Yeah, I will go to first slide. Yes.
Yeah. Thank you.
Anthony.
So whenever you are ready, I am ready.
Yes sir. 4:15 ಅಂತ ಹೇಳಿದ್ದೀರಾ?
Sir, ಹೇಳಿ sir.
4:15 ಅಂತ ಹೇಳಿದ್ದೀರಾ ಹುಡುಗರಿಗೆಲ್ಲ?
ಇಲ್ಲ ಸರ್, 4 o'clock ಅಂತಾನೆ ಹೇಳಿದೀನಿ. ಎಲ್ಲ ರೆಡಿ ಆಗಿದ್ದಾರೆ, ನಾವು ಸ್ಟಾರ್ಟ್ ಮಾಡಬಹುದು.
ಮಾಡ್ಬೋದಾ?
ಇದರಲ್ಲೇ 12 ಜನ ಇದ್ದಾರೆ ವ್ಯೂವರ್ಸ್.
ಸರಿ.
ಯೂಟ್ಯೂಬ್ ಅಲ್ಲಿ ಒಂದು 10 ಜನ ಇದ್ದಾರೆ.
ಸರ್, ಹುಡುಗರೆಲ್ಲ ನಿಧಾನಕ್ಕೆ ಜಾಯಿನ್ ಆಗ್ತಾ ಇರ್ತಾರೆ. I will just introduce and then we can start presentation, sir. Good evening. Namaskara. Welcome to the webinar, sir. Krishna Prasad, sir. on behalf of KSTA, hearty welcome, and I'd like to thank you for joining for this webinar. Let me have the privilege of briefly telling the achievements of Professor S. Krishna Prasad sir, who is the Honorary Scientist at Center for Nano and Soft Matter Sciences, Bengaluru. Sir has done his Master's Physics from Bangalore University and then pursued PhD in Raman Research Institute, Bangalore. Professor Prasad has made outstanding contribution of fundamental significance to the field of liquid crystals, fascinating class of soft condensed matter with path-breaking work on photo-stimulated effects, systems in confined geometries, as well as in the current hot topic of nano-soft systems, opening a new vista of novel composites. Professor Prasad has published over 300 research articles in national and international journals of high repute with high impact factor and has several patents for his credit, apart from handling many scientific projects, including those funded by the industry. For several years, he has led science outreach programs of the Center for Nano and Soft Matter Sciences, Bangalore. Sir has always been very kind enough to accept our invitation to deliver talks. He has delivered many talks for from degree to PhD level students, and he is an excellent speaker. He will be speaking on spectroscopy and the periodic table today, and I'm sure few students will be highly benefited by Sir's talk. With this brief background, I request Professor Krishna Prasad sir to take over and deliver his distinguished talk. Over to you, sir.
Thank you very much. At the and you put some embarrassing words there as well. So therefore, have to live up to some of the words that you mentioned. At the outset, I'm grateful to KSTA and especially Dr. Ramesh for giving me this opportunity to speak to you about the periodic table. The title that I have given, at least the first part, may look somewhat strange. And before I explain that, I want you to look at the two images. They are blurred, specifically made blurred because I didn't want a great reading to be done into those images. But on the left, you see some scrollings actually. And on the right side, you see a regularly arranged period. So the one on the left is the one that Dmitry Mendeleev made the periodic table in this fashion. It was not put in a regular table format during his time. I mean, when he made this, when he presented the world with this kind of a table. So as would get reflected in any research notes of any respected researcher, this is how things get done. You don't get everything well set into a nicely put table or any other document that you are doing in the first place itself. There would be a lot of crossings or scratches, as probably you would see here. These kinds of things, or there would be some deletions, additions, etc. Typical of a researcher's note. This is how the periodic table was made. But on the right side, you see something like 150, 152 years down the line that we have the modern periodic table where everything has been put into a proper place. And it's a very revered table that is found especially in all chemistry labs all over the world. Chemists vouch by these tables and the properties of the elements that are represented in those. In fact, in 2019, the year was referred to as the International Year of the Periodic Table. IUPAC celebrated this year as the International Year of the Periodic Table. And there were a lot of lectures, demonstrations that were held, even in Bangalore, even in our center, about the periodic table and several aspects of the periodic table. So with that, let me now say something about the title itself, because that's what I promised that I would be doing immediately after this. So what have I called it? The second aspect is easy to understand, spectroscopy and the periodic table. But I have said lead kindly light. In fact, this part of the title has been whipped from the title of a poem of the 19th century poet, John Newman. And this is pretty familiar to people in English literature, lead kindly light. Amid the encircling gloom, lead thou me on, and so on it goes. But to people who follow Kannada literature, and especially of people of my generation, this is a very well-known poem which was translated to Kannada by the erudite professor B.M. Sri, and it reads as Karunalu Ba Belake. So, in fact, the kind of point that I'm trying to stress is how important light, or rather the wavelength discrimination of light, referred to as a spectroscopy, an important role that it has played to put periodic table the way it is today, that we see today. So spectroscopy has played a big role, and that's what I want to emphasize throughout this talk. And I want to convince you towards the end of the talk that the game was actually very well set because of the presence of spectroscopy. So that's the kind of thing that I want to do throughout this talk. But before I actually get into that, I want us to appreciate the importance of the periodic table in a different context. Here, what I have done is the abundance of the different elements in three different contexts. One is the universe itself, and the second one is how the elements are present in the Earth's crust, and of course the third one, life itself. So let's look at the first one, the universe, and what you see is actually probably only two elements dominate the entire universe: hydrogen and its younger cousin, helium. In fact, they occupy about 98% of the total constitution of the universe. Oxygen takes 1%, which makes it about 99. So the rest of the elements that we are talking about, they occupy this minuscule part of only 1%, is all the elements that we know in the universe. The rest of it is hydrogen, helium plus oxygen. So that's the story for the universe. But if you come to the Earth's crust, things are slightly different. Now oxygen takes the major cake. Silicon has a substantial presence. Of course, down from aluminum, iron, calcium, etc., it becomes smaller and smaller percentages. But apart from these few elements that I have shown here, the rest of the elements, 100 or so, they form an extremely small concentration. They are present in traces, I would say, in the Earth's crust. And this is true not only in the Earth's crust, but in life as well as or in living forms such as a human body, for example. Again, oxygen, carbon, and hydrogen, they are the major constituents, and the rest of it, again, smaller and smaller concentrations. But one should not be neglecting their smaller presence. And just to give you one example, let's take a material like magnesium. Magnesium, an element, per day intake recommended for a human being is something like 400 milligrams of magnesium. 400 milligrams compared to the weight of the person, let's say it's anywhere between 50 and 70 kilograms. We are talking about 400 milligrams of magnesium. But the importance cannot be downplayed. It plays an important role. It controls, magnesium controls about 300 biochemical reactions and a host of other functions, including helping to steady the heartbeat. So the importance of each and every element is what the periodic table is about. And so therefore we can look at periodic table in its entirety and see how it has come to play a role in the world itself. So let me start with a formal slide called the outline of the slide of what I'm going to present. An introduction of 1 or 2 slides. And then actually my idea is to go around in a storytelling manner. See, I'm already an old man. So therefore, I should be telling stories. So therefore, I would go in a storytelling mode. And the very first story is about something that we are all very familiar. In fact, science students must be very familiar with this. If you have entered the chemistry lab, you would know this. That's the kind of thing that I am talking about. So it's a gas burner and the elements connected with that. And in fact, it has also a connotation, it has also a connection with something totally different. Physics people probably would appreciate this, something called network analysis, something that somebody who was teaching electricity or electrical networks, electrical circuits, that person would have taught you this, something called network analysis. So although I'm talking about gas burner and the elements, I will also bring a connection to this through a person who is well known for network analysis, and for him, the analysis was a child's play. So the second story that I'm going to start with is about the title, at least that I have given, is The Lazy but Noble Larks. Please remember the kind of spelling that I give for Nobel. There are two possible things depending on what you are referring to. Nobel is about the prize, because Alfred Nobel, his name was spelled as Nobel. But we are also talking about Noble, something which is different from the commons. That's what we mean by Nobel. So I'm going to talk about the Nobel laureates as well. And of course, I'm going to indicate an Indian connection to the periodic table in this regard. But then the third main story that I will be telling is about a person who laid the basis for the modern periodic table. So obviously, which means that the other two stories are in the preparation processes of the periodic table as we see it today. So whereas this one is how we see the periodic table and what's the basis that he found, an extremely important basis he found to put modern periodic table on a very firm basis. This is what I'm going to talk about as the third story. And maybe if time permits, I'm going to include one or two more stories. But then I'm going to end with something that I want to call as a postscript itself. So let's begin our storytelling journey. Let's start with this colorful slide, at least one picture which is colorful. It is nothing but the fireworks. And who doesn't love such fireworks? A lovely demonstration of how color comes out in its splendor all over the sky is something that at least during the Diwali times that we enjoy. Although this time I didn't see so much of a firework as in the previous years, maybe for good, maybe for bad. But let's go back to these fireworks, and there are documented records which clearly indicate that at least by 14th century, the Chinese, at least, if not anyone else, Chinese had a good knowledge of the recipes of chemicals or the additives that they had to add to gunpowder to get these spectacular colors. So, but by now, at least in the 21st century, we have a very well established, very well developed correlation between the element that we need to have and the kind of color that we want to realize. So in fact, alkalis, and some of those I have shown here, alkalis and alkaline earths are the favorites here to realize the kind of color. And you see some of the elements that are being put here, like sodium, lithium, barium, strontium, etc. So they all play this important role in giving us the kind of color by the presence of a particular chemical. So obviously what one would be leading to is how this color element correlation is established. So this is what actually takes us to the first story, which I have called as the gas burner and the elements. So this is something that I said, which chemistry student has not seen this? If the answer is no, I would be too surprised, right? This is a so-called Bunsen burner. And probably, I don't know whether your teacher told you, then the part Bunsen actually is the name of the person who made a significant contribution to make it appear the way it is today than the one that he was presented when he started his work on this Bunsen burner. In fact, the history tells us that Robert Bunsen, this is the picture of his, way back in about 1855 or so, he moves to the University of Heidelberg. He's given the assignment of setting up the chemistry lab over there. And just then, probably a year or two before, Heidelberg, the city in Germany, they would have taken a decision, a policy decision, that the entire city will be lighted up using coal gas. So therefore, their insistence that even this lab that Bunsen would be setting up should use only coal gas and nothing else for energy purposes. So he is given this task, and of course, the idea that he has as far as his chemistry interests were going, his goal was to study the colors of light emitted when different elements were heated up. But he had already observed by then that a burner that was present those days, it used to generate sooty flame. Soot, as you know, is emission coming from carbon, presence of carbon. So a sooty flame burning yellow due to the presence of carbon. Of course, this won't serve his problem, his chemistry interest at all, because he wanted to study the color emitted by the element itself. So therefore, in the presence of carbon, the incandescence that comes from carbon when carbon atoms are heated to high temperature, that masks, because this is coal gas. So it's predominantly carbon atoms which are present. So therefore, if they are giving out their incandescence, that dominates the color that comes out of the system. So it would be different to observe, it will be difficult to observe any color that a particular element presents in a much smaller concentration. That to be observed is a difficult thing. That's what his problem would be. So therefore, his goal now is to look for a burner, a device that would produce a flame with very little soot. That's the kind of goal that he has, very little soot. So he already knows the kind of solution. The aim is now to maximize the temperature, but minimize the luminosity. This luminosity is directly related to the incandescence that we are talking about coming from carbon atoms. That had to be minimized. But probably you may be familiar with the Bunsen's name, but probably your teacher might have missed telling you underneath, and you are supposed to, it is a knurled knob, you are supposed to rotate it to control the kind of flame that you get, right? And probably to begin with, the flame would be something like this, deep yellow kind of thing, and the teacher won't like the kind of flame. So probably you're supposed to tune and rotate the knob such that you would end up with this blue, beautiful flame that you see. So this is the kind of flame that Bunsen finally started his work and started identifying elements by looking at the kind of color that gets emitted. In fact, he's credited to have discovered two elements, important elements from today's point of view, also cesium and rubidium. And you should actually understand the kind of difficulties that people had in working in those days. I'm talking about the early 19th century. So therefore, the difficulties were the cesium actually that he discovered was extracted from the water in a pond that was found in a nearby place. So the water was taken out, and then one starts distilling it to end up with the kind of element that one is trying to look for. And here, in the case of cesium, Bunsen and his collaborators had to distill something like 44,000 liters of water to get something like 17 grams of cesium. Look at the phenomenal amount one starts with, 44 kiloliters of water, and finally end up getting only 17 grams of cesium. That's the kind of difficulty and that's kind of tenacity of purpose that they all had to come up with the beautiful results that they have been credited with today. So therefore, this is no different in any good research lab. Unless you work seriously on something, unless you put all your efforts, the fruits won't come out very well. So this is a good example of such a kind of effort associated with the kind of research one needs to be doing. But he had a nice collaborator. See, Bunsen was a chemist, and he had a nice partner in the form of a physicist actually. His name is, again, another Robert, but his first name is Gustaf Robert Kirkhof. So now if I tell this to any student who has cleared a 10+2 or a PU kind of exam, that person would know this name very clearly and immediately as well. Kirchhoff is something that we are all familiar when we are taught electrical circuit analysis. But probably you would be surprised that we struggle with these kinds of circuit analysis. But then for this man, it was a child's play, in the sense that he was just a student then, and then his teachers would have had asked him to give a seminar on some topic. And this person just doesn't take something from Google, of course not Google those days, but from textbooks or something like that, copy paste kind of thing. He didn't do, but rather he made a profound analysis of how circuits should be analyzed, and then came up with this new way of doing a network analysis. And that's something that he presented as a student, as a seminar topic. And that's something that we are all taught today, of how to analyze electrical circuits, and that they are employed even in extremely complex architectures of even making chips or integrated circuits. The same network analysis plays a very big role today. So this is the man, and probably you would be surprised what kind of man he could be, who works on electrical circuit analysis, and then how he could be contributing to something about elements, discovery of new elements, or periodic table or something like that. But you would probably be surprised that this man has made extremely good contributions in 3 seemingly different kind of topics. One, of course, we have already mentioned that, are the circuit laws, electrical circuit laws. The second one is also well known, something called laws of thermochemistry. I won't go into that. The last of the one is of interest to me today because he made 3 laws of spectroscopy. So let's look at those laws and then talk about the kind of contribution they have made to identifying the elements. Sorry, I'll take a sip of water. Sorry about that. So the kind of thing that Bunsen presented him were these kinds of things. He would be looking at different elements. Please look at these. These are halides. These are chlorides of lithium, sodium, potassium, rubidium, cesium, right? But when they are subjected to this heating by that strong flame that I showed, they emit characteristically different colored flames. So Bunsen wanted to know whether it is possible to very clearly associate, find a correlation, extremely good correlation between the element that is present, apart from the chlorine that is there throughout. Apart from that, Another element is associated, how to uniquely identify just by looking at the color of the flame. This is the problem that he would have discussed with Kirkhof. In order to answer this, as if to answer these things, he came up with these three laws. The first law says a luminous solid or a liquid or a dense gas. A dense gas is a gas which is subjected to high pressure. So therefore, the molecules or the atoms in the gas would be very close to each other. They would be in proximity with respect to each other. So if you take a spectrum of such a material, a solid or a liquid or a dense gas, what you end up is a continuous spectrum. Entire VIBGAR continuously varying from one end to another. The second law says this is now still a hot gas, but it's a low density one. What do I mean by low density? The constituents are now not too close to each other. It's hot gas, but it's a low density one. So then it produces a series of bright lines, but characteristic of the chemical content. A hot gas emitting light, it would consist of series of emission lines, but the pattern is now a line spectrum, like a continuous spectrum that we had previously. And now the kind of lines that you get are supposed to be characteristic of the chemical content. This is an important aspect that Kirkhof identified. Third law is now, let's say we have a cooler version of the same gas. We had a low density gas, a hot one previously. Now we have a cooler gas. Now you do not get bright lines. You still see an emission which is now a continuous spectrum interspersed with dark lines. Okay, so now you are talking about an absorption spectrum, in fact, and so therefore, what Kirkhof had already noticed was this emission spectrum and this absorption spectrum are pretty well correlated, or the wavelengths at which you see a bright line here is the same wavelength at which you would see a dark line when the gas is colder. This is the kind of absorption that he already has. And his argument was that these two patterns, the emission and the absorption spectrum of the kind that I showed, they are characteristic of the element present. And so therefore, it would serve as a fingerprint for the kind of element. In fact, it is the same principle that we employ even today. And here is something called a flame photometer, a very sophisticated apparatus by today's standards, which actually helps to identify the elements through this process of spectroscopy color correlation. So let's now apply these three laws to a celestial problem. What do I mean by celestial problem? Something that we notice up in the sky. Let's take the example of sun, an important celestial body as far as life on Earth is concerned, of course. So now, let's take the first example. The temperature of the sun, at least the surface of the sun, is about 6,000 Kelvin. And now between the sun and the observer here down on the Earth, you have cooler gases, right? A cooler gas actually surrounds a hot body. So what do you see here? Going by what I described previously, you would see dark lines interspersing a continuous spectrum that I have here. This is the same spectrum that was observed about, I think, 50 years before by another person called Fraunhofer. In fact, they are referred to as the Fraunhofer lines coming from a solar, coming in a solar spectrum. So dark lines interspersing a continuous spectrum. In fact, this is how today astronomers can accurately tell the chemical composition of a distant star. So what do? They do an experiment down on Earth. They know the kind of material that one has. So therefore, they can observe the emission lines giving bright lines on a dark background, so they know which element they are working on. And they now compare that with the Fraunhofer pattern that we showed previously, and then they can now correlate the two and then find out which element is actually responsible for the kind of spectrum that one is observing. This is exactly what Kirkhof did, and in collaboration with Bunsen showed that the sun contains sodium. So it's true with hydrogen as well. So for an astronomer, this is a beautiful tool, because now one is talking about celestial bodies which are millions of kilometers away from us. And sitting here on Earth, just using a telescope and a good spectrometer, one is able to say what kind of an element must be present in those celestial bodies. So it's as if I should be saying that Bunsen and Kirkhof found a new business for the astronomers, so that they can come up with all their spectroscopic analysis and say what is the constitution of a particular celestial body that they are talking about. So much so for the first story, wherein spectroscopy correlation came out in a beautiful way. Visible spectroscopy and identification of elements is what the contribution of Bunsen and Kirkhof that we can never forget about. So the next story, I have titled it as The Lazy but Nobel Laureates. Two characters are very important for this one. I have named both of them there. One is Sir William Ramsay, and the second one is Lord Rayleigh. In fact, the importance of this topic is clearly shown in the second line over there. I've said that they shared the Nobel Prize in 1904, the first for any Britisher to get a Nobel Prize in sciences. So they got the Nobel Prize for the kind of work that I'm going to describe. So since I said that this is more like a story, so or a drama if you want to call it, I've called it a scene one, act one, scene one, as you would see in any kind of a drama. So what is this scene? These two are the characters that I've already mentioned. The one on the left is Ramsay. The second one on the right is Lord Rayleigh. Act 1, Scene 1, 19th April, 1894. Rayleigh would be giving a lecture to the Royal Society. And the title of the talk is On the Composition of Air. Look at the kind of title those people had, and those years one could have. Very simple and very profound as well. So, which means that till about 1900s, at least, people didn't understand exactly what air that surrounds us. The constitution of air was not clearly known. So, 1894, the title says On the Composition of Air. One of the persons who would be attending this is Ramsay. He would be sitting in one of the front rows and describing the kind of work that he had done. And he had previously published in just a couple of years ago, Rayleigh had published this in Nature, a very celebrated scientific journal even today. And the title of that particular article was Density of Nitrogen. In fact, towards the end of the talk, Rayleigh, or his given name is John William Strutt, but he was also among the Nobel Nobel people in England. So therefore, he already had the title Lord, and that's how. And he's from a place called Rayleigh, and therefore he is referred to as Lord Rayleigh. Actually, his given name, as I said, is John Strutt. So Lord Rayleigh comments that I am much puzzled by some recent results as to the density of nitrogen, and look at the kind of humility that the person has. He's not audacious. He's not showing off his knowledge. He requests, I shall be obliged if any of your chemical readers, please remember, Lord Rayleigh was a physicist. I shall be obliged if any of your chemical readers can offer suggestions as to the cause for the observation that I have. And what is the observation that he is referring to? or the puzzle that he was referring to? He was referring to the discrepancy between the density of nitrogen made by chemical synthesis and nitrogen isolated from air by removal of other known components. That's the key word here, known components. People used to extract these things from the air around, and they used to take our components and then look and analyze at what's happening. So therefore, he finds a discrepancy in the density between the nitrogen that was made in the lab and the nitrogen that was isolated from air by removing the components which are already known. So, but please remember, when I'm talking about the discrepancy is a very small one. It's something like 0.1% or 1 part in 1,000. Oftentimes, not so serious researchers would probably push this under the carpet and saying that maybe I didn't take a proper reading kind of thing. But Lord Rayleigh was a very good experimenter, a very serious experimenter, a very systematic one. And so therefore, he had already ruled out that this difference is beyond the errors of the experiment that one carefully performed. So therefore, he was certain that this discrepancy indeed exists. So Rayleigh points to this question and says that, is it possible, because of the contamination of the synthesized gas, of the synthesized nitrogen, has it got contaminated by a lighter gas? And is it the reason that I'm finding this discrepancy in the density? Ramsay, who would be sitting in the audience, as I told you earlier, makes a very cryptic remark. He says, why not the opposite? By that he means there could be a heavier impurity in the atmospheric one. In fact, you can probably say that just to make fun of what Lord Rayleigh proposed, Ramsay could have said this. No, it was an intelligent answer, in fact, because Ramsay would have read in detail what Cavendish had published about a century before. Cavendish, the same Cavendish that is well known for so many experiments on different things, including on air. This Cavendish would have published in Philosophical Transactions his experiments on fictitious air. And so therefore, he would have raised several important questions on the observations that he has made. And Ramsay is very familiar with the Cavendish experiments. And having that in mind, making a 2 + 2 of what Rayleigh proposed, or seemed to pose a question, and what Cavendish had raised as possible questions, Ramsay would have put the two together and would have raised this question of why not the opposite, heavier impurity in the atmospheric one. So see, this is what happens even today. A person attends a conference, gives a lecture, somebody in the audience gives or makes a comment or raises a question that puts the speaker as well as the person who would have raised the question to serious thoughts about what is the science involved here. Okay, please remember, Ramsay is a chemist, Rayleigh is a physicist, but they still forge a collaboration between the two teams. This is truly interdisciplinary that way, that we all claim today that we are working on interdisciplinary subjects. Even those days, people could come together and forge collaborations, although seemingly working on totally different topics, a chemist and a physicist, not having many things in common. This whole thing is about, the story I can probably express in terms of a Kannada proverb. Kannadadalli ಒಂದು ಗಾದೆ ಹೇಳ್ಬೋದು. I don't know how many of you don't follow Kannada. If not, probably you can seek the help from somebody who speaks Kannada in your neighborhood. There is a proverb which says, ಸುಮ್ಮನೆ ಇದ್ದವನನ್ನು ಬ್ರಹ್ಮನು ಗೆಲ್ಲಲಾರ, which actually means, or probably translated to what I'm talking about today, it says that if you don't react, you can't be won over. No struggle actually can be won against a person who doesn't react at all, right? This is true even in our daily life. So therefore, this problem actually is true in this particular situation, because in those days, in Mendel's times or in Rayleigh's times, identification of an element was very tough. In fact, their predecessors, if you take Cavendish's time, for example, people used to use sensory organs like lick an element, smell an element kind of thing, and then find out what the composition is. Sometimes it led to disastrous results, because what the person probably is trying to taste or smell could be a poisonous material, and so therefore there could be fatal results. But anyway, things had improved by the time these people came on the scene, and what one had to appeal was to have chemical interactions, chemical reactivity of the suspected element, and then find out how it is reacting, and then find out what is the chemical composition of the element one is working on. So imagine the plight of these people. They were actually, if I may let the cat out of the bag, as they say, if I may tell you what I'm looking for in the next couple of slides, they were looking for a material, an element which does not react at all. The absence of reaction, absence of chemical reactions for such materials is the serious problem in this case. And so therefore, that should tell you the importance of the kind of work that they did. So as I already said, they form a collaboration, the physicist and the chemist. Please note the month, August 1894. This I have called scene 2. Scene 1, we saw what happens during the Royal Society lecture. Scene 2, 4th of August. I'm running it like a calendar now. You please pay attention to that. 4th of August, Ramsay isolates the new gas. Please remember, he had commented that there could be a heavier contamination in the atmospheric air. So therefore, he would have worked on that. And therefore, he and his team would have isolated this new gas, and the kind of effort that they would have put is unimaginable. Single-minded determination is something that probably can describe the kind of effort that they have put, because between the lecture and the date where this communication from Ramsay goes to Rayleigh is only 4 months. Within 4 months, Ramsay is trying to prove the point that he made during the lecture. That is, in fact, a very serious piece of research work. Okay, Ramsay writes a letter. Please remember, those days, no WhatsApp, no Google, no Gmail, nothing of the kind. So everything had to be through what you people call as the snail mail. Okay, in his own handwriting, Ramsay would have written on 4th of August, dear Lord Rayleigh, I have isolated the gas. Its density is so much, so and so, and it is not something, etc., etc. This is the kind of communication, a private communication from Ramsay to Rayleigh. Happens 2 days later, 6th of August. 4th of August, Ramsay's letter. 6th of August, Rayleigh replies to him, I too have isolated the gas. But look at the second part of that sentence, though in miserably small quantities. Okay, he is already talking about how minute this content could be. But please remember, Rayleigh is a physicist, so you can pardon him, because as far as extraction of elements or materials are concerned, it is too difficult for a physicist to beat a chemist. A trained chemist like Ramsay is any day far good compared to a physicist like Rayleigh. So you can pardon him, but the importance is that it's a reproducible result. 2 different labs, 2 different kind of skills that people possess, and they isolated the same gas, although it exists in minute quantities. But now they had to take the help of a spectroscopist. This is where actually the title actually merges with what I'm talking about. Without spectroscopy, these people could not have announced to the world what they announced on 13th of August the same year. Just a week later, 6th of August, Rayleigh writes this. A week later, these 2 guys announced to the world the discovery of a new element, argon. They named it as argon, which means the lazy. The lazy highlights its non-reactive character, non-chemically reactive character. And in fact, much later, a series of elements, series of gases, I should say, like argon, they came to be known as the Nobel Gases. In fact, now is the pun, now is the play on words. This discovery of a noble gas, the first noble gas to be discovered, so got these two guys their Nobel Prizes. That's what happens when you do a Nobel job. So they would have sought, as I said, help from a spectroscopist in the form of Sir Crookes, who would have used the Kirkhof method to provide the spectroscopic evidence to say that this is indeed a new element that has not been discovered till now. You know, scene 3 actually is something that goes against these two guys. Skeptics are always there when you make something earth-shattering kind of discovery, because there is no precedence, there is nothing known about such things, and so people don't easily agree with what you do. That's what the doubters or the so-called skeptics do. And if you have an ordinary skeptic, it's okay. But if you have the master of the elements, Mendeleev himself didn't believe that Ramsay and Rayleigh had a new element in their pocket. Okay, there was of course also Dewar to join the team of skeptics, and so therefore there was a serious issue that was raised against these two guys, Ramsay and Rayleigh, saying that no, I don't think you have a new element there, and these people would be saying that you are just misled by something. It is not a new element at all. There was a reason for Mendeleev to say that, not jealousy or something like that, not human fallacies, but the reason is the kind of periodic table that he had made was based on chemical reactivity. So if something doesn't chemically react, it has no place in his periodic table. So therefore, he didn't just believe that there could be an element called helium. Of course, the spectroscopy evidence that they have provided was irrefutable, was undoubtful. In fact, I can show the spectrum of argon here, and there are series of lines here which stand out. I won't go into the details of how they stand out compared to anything that is known till then on Earth. And so therefore, they did have a good proof, but Mendeleev didn't believe in the proof. In fact, let me take out something here. I don't know how to do that. I had a file here. Sorry. Trying to rise if possible. I wanted to read something out. The kind of remark that Mendeleev made. Just give me a minute, please. Yes, here I found that. Mendeleev would have given a talk to the same Royal Society earlier in 1889. And this is a Faraday lecture, a very celebrated lecture, very honorable kind of thing. And Mendeleev would have said, from all sides, we see attempts to constitute the imaginary substance helium. I'll tell you how even before Ramsay and Rayleigh made their presentation, how did Mendeleev came to know about helium? I'll come to that in a minute or so. But he would have already quipped on this. He would have already commented on this. Substance helium, the so much longed for primary matter. No attention is paid to the circumstance that the helium line is only seen in the spectrum of solar protuberances, so that its universality in nature remain as problematic as the primary matter itself. Nor to the fact that the helium line is wanting amongst the Fraunhofer lines, etc., that he goes on, and because of his strong belief that there can be nothing, no element which does not chemically react at all. And this is what actually would have made him to make such a remark. So this is what they had done. 5 intense months of research, pakka spectroscopic evidence, and they would probably shut down the doubters, except for Mendeleev. Dewar, etc., would probably agree with the kind of evidences that Ramsay and Rayleigh further provide after 5 months of intense research. And Ramsay becomes bolder, and he gives a lecture to the Royal Society again on 31st of January 1895. Please remember, 1894, early 1894 was Raleigh's lecture. Just about a few months later, they provide a pakka evidence to the Royal Society. There is argon, a new constituent of the atmosphere. The importance of helium actually comes into the picture here. Argon was to be followed by helium. And so therefore, this makes it all the more attractive that people had found a noble gas, a new noble gas, and it was already contained in the atmosphere. Among the noble gases, there was already a discovery, but what we should be talking about is that this element is the first alien element to be discovered. What do I mean by alien element? It is an element which was not found on Earth first, but in a celestial body. In fact, in the sun. And the person responsible for this is Pierre Janssen. That's how his name is pronounced, Pierre Janssen. And Pierre Janssen is not a chemist, is not a physicist, but he was a stargazer. That means he was an astronomer. And his idea was to do solar spectroscopy. And he would have thought that to reduce the atmospheric noise, it is better to do the solar spectroscopic measurements during a total solar eclipse. And this is where the first Indian connection that I mentioned earlier comes into picture. 1868, there was a total solar eclipse, and India was the best place to observe this total solar eclipse. So Janssen comes down all the way to South India, to Guntur, a place which is not too far from Bangalore. He comes to Guntur, and he would be making his observations of the total solar eclipse there. And he finds an additional bright yellow line whose wavelength did not match with any known element. These are the observations of Janssen. Okay, he says an additional bright, which is called the D3 line today. It is not, it doesn't match the wavelength of any known element, and so therefore there is something fishy happening here, and this could be because of a new element that is present at least in the sun. Janssen doesn't commit anything on what could be happening on Earth or any other place. He says sun at least contains a new element which is not known till today. Norman Lockyer, a Britisher, would also be doing a similar kind of observation, but he didn't come down to India, but he would be sitting safe and nice in his home in England, and he would be observing the same eclipse. And so he would have also made the same observation that there is a new line there, but he goes one step beyond Janssen, and he calls it as helium. Helium because helios is sun, and this element, this spectroscopic line was found, this anomaly was found in sun, and so therefore he calls this element which could be responsible for that to be helium itself. Dr. Ramesh?
Sir.
I would be needing about 10 to 15 minutes more. Is that acceptable?
Oh, sir.
Hello?
Yeah, please go. Please carry on, sir.
Okay,
no problem.
great. Yeah, when I get into the storytelling mode, I usually miss my durations. So sorry for that. Okay. So, of course, Ramsay isolates it. He is now actually a master of extraction of elements from different constituents. And of course, there is also another tangential kind of proof to say that helium existed on Earth. There is an volcanologist by name Pomeroy who would have found helium in the lava of Mount Vesuvius, but then he wouldn't have made clear observations. So therefore, that is lost to the world. But when Ramsay comes on the scene, now he has this spectroscopic tool, beautifully prepared by Crookes, And then Ramsay's team would have mastered of how to do elemental spectroscopy. And then they do find that this new gas that they have extracted, which matches with the spectrum found by both Janssen as well as Lockyer, they match very well. And so therefore, they identify this new element, the so-called helium, by the D3 line that is present in the spectroscopic in the spectrum of this particular element. So therefore, this clearly establishes the importance of spectroscopy, of how element of element can be easily identified just by doing using spectroscopy as a tool. In fact, helium is an important component, as we know today. It is the same helium that is used in birthday party balloons. It was so well established by Ramsay. Please remember the years. We had talked about 1895. Okay, argon in 1894, helium in 1895. Ramsay's team is working overtime. They're very enthusiastic. They are going full-fledged on their discovery of elements after elements. In fact, any team would have been happy and rested since they've already discovered two elements. Discovery of one element itself is difficult. And they've already pocketed two elements in 2 years. And what more you want? You go and enjoy, do a party kind of thing and forget about science. This is not true with Ramsay's team. Ramsay's team works overtime, as I said. In the space of only 4 months, this group discovers not one but 3 new elements. Neon in June 1898, krypton in the same month, couple of months later, September 1898, xenon. So you have argon, helium, neon, krypton, xenon. If you look at the periodic table today, you see that they almost occupy an entire group. It's as if out of courtesy, they left the last one in the group, radon, naturally occurring, of course, radon, to a different team by Frederick Dawn. 1900, he discovered radon. It's as if just by courtesy, they left for him to identify the thing. I want to emphasize one particular point before I go to another story. This is about the kind of task, the uphill task that they had in identifying any of these elements. Let me give the atmospheric constitution of these elements. Argon, 0.93%, helium, 5 parts per million, which means that if there are 1 million atoms of air, you will have 5 of them being helium, 5 out of 1 million. Neon, 18 ppm, 18 parts per million. Krypton, 1 part per million. Xenon, the worst of the lot, it is 90 parts per billion now, which means that if there are 1 billion atoms, xenon constitutes only 90 of them. Such a tremendously small concentration. And in addition to the fact that they're all chemically non-reactants, they become liquids or solids at extremely low temperatures. They are colorless, they are odorless, they are tasteless, as well as monoatomic. All this increase the complexity in discovering those things, and this team did a splendid job of that. It is here that there is a second Indian connection, a more robust one that I want to mention in half a sentence or 2 sentences at best, and then go to the next topic. The second Indian connection is about the establishment of the Indian Institute of Science. The Tatas want to establish an institute of excellence, institute of research excellence in India. So therefore, they would be hunting for a suitable location as well as somebody who can head that. The suitable location problem was solved by the Maharaja of Mysore, who donated the campus that where the Indian Institute of Science stands today. They donated that land to the Tatas. And then the Tatas were also looking for a researcher who could head that. And so therefore, they would have written a letter to Ramsay, the Nobel laureate. If you have anyone in mind who can come down and then organize this new institute that we want to start, we would be extremely grateful. This is the letter that goes from the Tatas to Ramsay. Ramsay then, without a second thought, recalls Morris William Travers, a student of his who would have been completely involved in the discovery of all these noble gases, he would have observed him to be a very systematic, a master in systematic work, a person who is meticulous in his work, and then who can work extremely hard. So 1898, Maurice Travers would have got his PhD working with Ramsay. 1903, he gets an offer from University of Bristol, so he heads there. But then Ramsay calls him back saying that, no, you have a better job, go to India, set up this new institute. 1906, he comes to India to set up, he becomes the founding director of the Indian Institute of Science. And as you would see today, the Indian Institute of Science is perhaps the best possible research institute in the country, and this man laid the foundation for it to become a center of excellence. So now let me move to the third story, and paucity of time, so therefore I will make this the last story in my repertoire. And this is about the man who laid the basis for the modern periodic table. I would rush a bit here. His name is, the full name is given here, Henry Gwyn Jeffrey Moseley, born 1887. This is the person I'm referring to. And when he comes on the scene, he joins Rutherford's lab. When he joins the lab, X-rays were a very hot topic. Rontgen would have discovered X-rays. He would have shown the importance of what it means to have X-rays. And Loewe would have shown the diffraction of X-rays. Bragg and Bragg, the father and son duo, Lawrence and William Bragg, they would have shown the diffraction laws of X-rays. So this is a very hot topic. And that's when he enters the lab, Moseley enters the lab of Rutherford. So Rutherford would have assigned a topic to work on for Moseley. But Moseley is not so much interested in that particular topic. So in fact, one day he even writes a letter to his mother saying that oftentimes I'm not doing much research, but I'm tinkering the car of my supervisor. That's the kind of thing that he gets frustrated with, because this is the kind of question that he wanted to address. Are there better alternatives to atomic weight as the basis for the periodic table? That's the kind of thing that this person wants to work on. And it so happens that he had a couple of interactions with very important people, including with one Dutch economist by name Brock, economist, not a scientist, but he was an amateur scientist who would have suggested that there must be a new fundamental particle called alphon, that's his name, charge +1 and mass of 2 units. This must be the basis for arranging the elements known. And then most importantly, Niels Bohr, who was already a celebrity, Niels Bohr would be visiting the lab of Rutherford, and when during a conversation with Moseley, he says, yes, man, I can understand the kind of frustration that you have, and I know what kind of work that you want to do. The degree of scattering of X-rays, according to me, should be proportional to the atomic charge rather than to the atomic weight of the element. If this can provide you any clue to do the experiment, I do want you to do the experiment and then prove me either right or wrong. Look at the audacity of this young person. He says, Moseley says, we shall see. In fact, by then he would have already started on something which is known today as X-ray spectroscopy, the presence of a line spectrum depending on the shell responsible for the electronic transition. So he constructs this beautiful apparatus, X-ray spectroscope, and using a ferrocyanide crystal grating in the place of prisms. Prisms, as you know, in the visible wavelength region, we use prisms to as a spectroscopic tool to split the white light, for example, into its components. The same thing can be done in the X-ray regime by using a crystal grating. And then most importantly, he created a sample train without breaking vacuum. I won't go into the details of the kind of apparatus that he had. And then using this kind of an apparatus, which is, I should call the birth of X-ray spectroscopy, he was able to demonstrate a beautiful law, probably one of the most fundamental things that you can find as far as periodic table is concerned. He was able to show the frequency here. Somewhere here I have a video. I don't know where it is. Yeah, here. I don't know whether the video can be seen here. Yes, you can watch something. He worked on an entire period of atoms, and then look at the kind of X-ray spectrum that he gets, and then he sees the beautiful correlation. The strongest of the lines actually forms a beautiful staircase going from one element to another in the period, and they form this beautiful law that he was able to demonstrate, and the step height is only one integer difference. So therefore, he was able to show, he was able to plot this beautiful diagram, square root of the frequency of the X-rays reflected from the element is proportional to, this is the charge, so Z minus 1 is the proportionality that he observes. So therefore, they fall beautifully on this line, and he was able to establish, since it was already known that this atomic charge should be related to the serial number. Please remember, when you make a list, you also put some serial number, right? This is the serial number that Mendeleev used. So therefore, he said, forget about this, man. Mendeleev, you forget about the atomic weights being the important parameter. It is a serial number which looks so innocuous, so innocent in your tables. It is that which is the most important parameter. The atomic number should be the basis for organizing the periodic table. By then, Rutherford would have proved that the so-called nucleus of an element is not just a blob, but rather consists of individual particles taken as to be the protons. And so therefore, the kind of atomic number that we are talking about is nothing but the number of the protons present in that particular element itself. So this gives a beautiful physical meaning as well as a nice basis for people to establish and make a good periodic table. In fact, again, astronomers gain nicely by the X-ray spectroscopy that Mosley came up with. Even today, they employ these kinds of things. And look at this 1994 kind of publication in a very respectable journal, X-ray spectrum of a supernova remnant Cas A, and they can identify each and every element that is present in the X-ray spectrum that comes out of such a material. So we can say that the modern periodic table is born. Okay, but this man is very young. 1915. Please remember, 1914 is when the World War started, First World War, the Great War as they call it, started. And this man is a patriot. And there would be a call to all British citizens, please help the war effort that Britain is in with this European country, Germany. So therefore, Mosley joins the army. He is posted to a place which is called Gallipoli in Turkey, and his brigade would be put on the war front. And Mosley, a radio engineer actually, he takes a bullet in his head and dies at a very young age of 27. This actually infuriated a lot of scientists, including Rutherford, etc. They wrote a very strong letter to the British government that scientists like Mosley should have been shielded from entering the war field like the way that he was made to enter. This is a big loss, not just for the country, not just for his family, but for the entire scientific community. A man at the age of 27, he had made such wonderful contributions. I don't know what kind of contributions he would have made if he were to live longer. In fact, because of this, a new group named as Group 8, or as we call it as Group 18, came to be known, and the Nobel Gases of Ramsey, they were provided a nice place. This solves in one stroke Mendeleev's version and the puzzles that were associated with the Mendeleev's version of the periodic table, and has put the periodic table on its grandstand today. I can go on like this, and I've already apologized to Dr. Ramesh that I have exceeded my time. So therefore, I won't go with the rest of the stories. I just want to quickly run through this postscript. Energy dispersive X-ray spectroscopy is something that people vouch by today pharma industry, the medicine making industry actually heavily depends on this energy dispersive X-ray. You talk to any nano scientist today, they all go by this what they call as EDAX, without which they can't be doing most of their work. And one corollary that I want to quote is, you might have wondered when you look at the periodic table today, that is there any limit to the kind of number of elements that you can have in a periodic table? And somebody asked this question to the most famous scientist of modern times, Richard Feynman, the Nobel laureate, and the maverick scientist he was. He answered, yes, there is a limit. You cannot cross 137 as the atomic number of any element because of the speed of light associated with the speed of electrons. I won't go into the details of what Feynman's arguments were. So therefore, if you find 138, probably you can name it imposium or imaginarium or an unobtainium kind of element that you can have. Lastly, I want to leave you with a very sobering thought. As human beings, we have bragged about, we have shown off the kind of knowledge that we have learned throughout the ages and what we can do, what we can discover, etc. But when you look up a clear night sky, the stars shining, and if you have time for that, you will lie on the rooftop looking at the sky and you see how miniature you are, how small you are compared to the entire cosmos. That's when you would realize that everything that you see on earth, everything that man tries to show that he has made it for the first time, the earth has a way of showing that it already knows it. So this is what I consider as the way that nature shows that it knows the periodic table. Here is a video. I hope that it comes out all right. So sorry. Yeah. Yeah, that's about the northern lights that you can find if you go to the northern pole. It's called Aurora Borealis, and there is an equivalent on the south pole called the Aurora Australis. So if you happen to go there, then you can record the time-lapse photography that I showed and made my own comments on that. And probably you can show, post me a better kind of video that I would be able to show to the next set of speakers, the next set of audience who are going to listen to this kind of a talk. Thank you very much. And thanks again to KSTA for this opportunity. And I would be happy to answer any questions that may be raised here. Thank you very much.
Thank you very much for a very informative and scholarly talk on periodic table. You spoke about the history and discovery of elements, different elements by various scientists, and some of their connection with India, especially the founder director of Indian Institute, M.W. Travers. It was really wonderful, sir. As of now, there are no questions.
Stop. How do I stop sharing? Okay, I do see here. Okay. Yeah.
Sir, thank you very much for a very informative and scholarly talk. I'm sure students would have any take-home messages from your talk, and we are very grateful to you for having accepted our invitation and delivered this wonderful talk. And the history of periodic table would certainly be of use to PU students. And finally, you gave how periodic table scientists who discovered periodic table, few of them had Indian connection, and the founder director M.W. Travers, how he was involved in the development of periodic table, etc. And as of now, there are no questions from participants. If they have any questions, I request them to put it on chat box. We will be sending it to you, sir, for answering later. So on behalf of all, thank you very much, sir. Hello. Hello. Thank you very much, sir.
Oh, thank you. Thank you very much. Thank you. It was a pleasure.
Nice talk.
May I sign off now?
Yes, sir. Yes, sir. Please.
Okay. Thank you.
ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರೇ, ನಾಳೆ ಟ್ರೂ ರೆವಲ್ಯೂಷನ್ ಬಗ್ಗೆ ಮತ್ತೊಬ್ಬ ಸಂಪನ್ಮೂಲ ತಜ್ಞರು ಉಪನ್ಯಾಸ ಕೊಡ್ತಾರೆ. ಡಾಕ್ಟರ್ ಶಿವಕುಮಾರ್ ಮಗದ ಅಂತ. ಅವರು ಅಷ್ಟೇ ತುಂಬಾ ಒಳ್ಳೆ ವಾಗ್ಮಿಗಳು, ತುಂಬಾ ಚೆನ್ನಾಗಿ ಮಾತಾಡ್ತಾರೆ. ನಾವೆಲ್ಲ ಈ ಒಂದು ನಾಳೆ 4 ಗಂಟೆಗೆ ಇರೋ ಉಪನ್ಯಾಸಕ್ಕೂ ಸಹ ಹಾಜರಾಗಬೇಕು ಅಂತ ಹೇಳ್ಕೊಳ್ತೀನಿ. ನಿಮಗೆ ಯಾವ್ದಾದ್ರು ಒಂದು ಸಬ್ಜೆಕ್ಟ್ ನಲ್ಲಿ ಉಪನ್ಯಾಸ ಬೇಕು ಅಂದ್ರೆ ನಮಗೆ ಚಾಟ್ ಬಾಕ್ಸ್ ನಲ್ಲಿ ಅಥವಾ ಇಮೇಲ್ ನಲ್ಲಿ ಅಥವಾ ನಮ್ಮ ವಾಟ್ಸಪ್ ಗ್ರೂಪ್ ನಲ್ಲಿ ತಿಳಿಸಿದ್ರೆ ಆ ವಿಷಯಕ್ಕೆ ಸಂಬಂಧಿಸಿದಂತೆ ಎಕ್ಸ್ಪರ್ಟ್ ಗಳನ್ನ ಇನ್ವೈಟ್ ಮಾಡಿ ನಿಮ್ಗೆ ಟಾಕ್ಸ್ ಕೊಡ್ಸೋದಕ್ಕೆ ಎಲ್ಲಾ ರೀತಿಯ ಪ್ರಯತ್ನ ಮಾಡ್ತೀವಿ. ಈಗ ನೀವು 10-11 ಜನ ಅಟೆಂಡ್ ಆಗಿದ್ದೀರ, ನಿಮ್ಮ ಸ್ನೇಹಿತರಿಗೂ ಹೇಳಿ ಈ ಉಪನ್ಯಾಸ ಅಟೆಂಡ್ ಆಗೋದ್ರಿಂದ ಅವರಿಗೆ ಹೆಚ್ಚಿನ ಒಂದು ಜ್ಞಾನದಲ್ಲಿ ಹೆಚ್ಚಿನ ಆಸಕ್ತಿ ಬರುತ್ತೆ ಮತ್ತು ಎಕ್ಸಾಮ್ಗೂ ಉಪಯೋಗ ಆಗುತ್ತೆ ಅಂತ ತಿಳಿಸ್ಬೇಕು ಅಂತ ಈ ಸಂದರ್ಭದಲ್ಲಿ ಕೋರ್ಕೊಳ್ತೀನಿ. ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು.